Assalamualaikum. Again, I'm going to continue with the second lecture of CHM477, and this lecture will cover valence shell electron pair repulsion theory, VSEPR. We have learned, I have shown you how, well, we did a revision on how to do Lewis structures for molecules, and you've done a few exercises as well on that one. So based on the Lewis structures that you drew, we can determine the shape of the molecule using the VSEPR theory, valence shell electron pair repulsion. Now, VSEPR states that pairs of valence electrons repel each other in space in 3 dimensions so as to be furthest apart as possible. So when you have more than one pair of electrons in the valence shell, those pairs will try to push each other away as far as possible to minimize repulsion, or to minimize repulsion. And the magnitude of repulsion is greater for a lone pair compared to a bonding pair. I have also covered how to distinguish between lone pair and bonding pair in the last lecture. A lone pair is a pair of electrons that is not used in bonding with another atom, whereas a bonding pair is a pair of electrons used to bond with another atom. Now, when a covalent bond is formed, it can be assumed that an electron from one atom pairs up with an electron from another atom to satisfy the octet for both atoms. This we learn in the octet rule. The shape or geometry of mean using the VSEPR, taking into account the number of electron pairs surrounding a central atom. Now have a look at this table. Now this table I take it from a Chang textbook. It is arrangement of electron pairs around a central atom A in a molecule, and the geometry of some simple molecule and ions in which the central atom has no lone pairs. So assuming that all the pairs in this atom or in these compounds or in molecules are bonding pairs. Now, if you go through this table, if there are two bonding pairs of electrons attached to the central atom A, this is one bonding pair and this is another bonding pair. The two pairs will push each other away as far apart as possible in space or in 3 dimensions. And in this case, the furthest apart two bonds can be away from each other is 180 degrees. So that is why this molecule is linear, because this bond is 180 degrees away from that bond. So you have a linear molecular geometry. Yeah, so that is very simple to understand. The example of that would be beryllium dichloride or mercury dichloride. Now, as we progress along, if you have three bonding pairs around the central atom A, so you have one bonding pair, two bonding pair, and three bonding pairs. The furthest away those three bonding pairs can repel one another is in this manner, where the angle between the two bonding pairs is 120 degrees. So in this way, you have a trigonal planar. You have a trigonal planar geometry like that. Planar means it is on the same plane. It's like on a sheet of paper. A is in the middle. One bonding pair is at the top here on the same plane. Another bonding pair is at the bottom. And another bonding pair is at the bottom. In that situation, you have a geometry called trigonal planar. Yeah, trigonal planar. Now progressing on, if you have four bonding pairs here, the four pairs of electrons will repel one another in space, and the geometry that is going to be achieved through that is called tetrahedral. Tetrahedral is when the angle between one bonding pair to another bonding pair is 109.5 degrees. That is an ideal tetrahedral angle. An example of that is methane or an ammonium ion. So just a recap, when you have two bonding pairs, linear. When you have three bonding pairs, trigonal planar. When you have four bonding pairs, you have tetrahedral. And in the same argument, or in the same line of thinking, five pairs of electrons around a central atom A will make this geometry where it looks like two pyramids, one at the top, one at the bottom, and the pyramids have a triangle base. So this is called a trigonal bipyramidal. Yeah, very simple. Two pyramids with a triangle base, one at the top, one at the bottom, with two different bond angles. On the horizontal, you have 120 degrees, and on the vertical is 90. So it's really very, very easy to imagine how these five electron pairs repel one another. And the biggest, most common number of bonding pairs around a central atom is 6, yeah, or the highest number. 6 is highest common number. So if you have 6 bonds around central atom A, the 6 bonds are going to repel one another, and what shape that you're going to get is called octahedral. Now, octahedral has the angles of 90 degrees in whichever bond you are looking at. From this vertical to that horizontal is 90. From that horizontal to that another horizontal is also 90. And from this horizontal to that vertical is also 90. So that is an example of octahedral, which is SF6 or sulfur hexafluoride. So octahedral looks like this. So you must be familiar with these shapes and be able to draw them and name them and state what are the angles, so you can determine the shape of your molecule. For example, a methane. Methane, everybody knows, it has 4 carbon to hydrogen bonds, and the 4 carbon to hydrogen bonds will repel one another to the most maximum possible furthest distance away, and the shape that it's going to assume or it's going to take is a tetrahedral shape. And PCl5 will take, for example, will take trigonal bipyramidal, and SF6 will be octahedral. So that is really quite easy. That is the basis of VSEPR, assuming that all your electron pairs are bonding pairs. That is the picture of what a linear looks like, a linear molecule looks like. That is the central atom, which at the top they call A, and this is another. This is atom, two different atoms. So that is linear, that is trigonal planar, that is tetrahedral, that is trigonal bipyramidal, and that is octahedral. So the electron group repulsion and molecular shape is presented in this picture. I hope that is okay, and you can follow this VSEPR theory very, very clearly. Now, what happens when you have a lone pair of electrons in the calculation? Table 10.1 at the top just now only account for all bonding pairs. Now table 10.2 account for bonding pairs as well as lone pairs. Now remember, lone pairs are electrons or pair of electrons that do not get attached to another atom. Yeah, do not get attached to another atom. That way, that is an invisible entity. You cannot see it. So if you have a situation where you have A as the central atom, B as the bonding electrons or bonding electron pair, and E as a lone pair of electrons, you have a total number of 1, 2, and 3 electron pairs. 3 electron pairs. There are 2 bonding pairs and 1 lone pair. Now, what is the shape of the molecule if it has 1 central atom, 2 bonding pairs, and 1 lone pair? So it is going to, if you still recall, 3 bonding pairs will take a square, not square planar, a trigonal planar shape. But imagine one of the bond is invisible. One of the bonds is invisible. Being lone pair, that lone pair is invisible. So in this situation, what you can see is just this B bonded to A and A bonded to B. What you cannot see is this very, very invisible lone pair of electrons. So what can be seen is just a band shape. Yeah. The arrangement of electron pairs is trigonal planar, but the geometry of the molecule is bent, and you have the drawing in this way. And remember, in the few minutes ago, I was telling you that the repulsion, the repulsion of a lone pair is bigger in magnitude compared to a bonding pair. So if the repulsion of a lone pair is bigger than a bonding pair, then you are going to have this invisible lone pair having bigger strength to push these 2 bonding pairs further away from itself. So if in an ideal trigonal planar you have 120 degrees here bond angle, here what you see is less than 120 degrees because this occupies a bigger space even though it is invisible. Yeah, are you following me? So a bent SO2 has a bond angle of less than 120 degrees. Now, if you take the next situation where you have AB3E, that means 3 bonding pairs and 1 lone pair of electrons, the 4 will arrange themselves in this way, in a tetrahedral manner, but the lone pair is going to be invisible. That is going to be invisible. What you are seeing in actual fact physically is a trigonal pyramidal geometry, where you have a pyramid, quite flat pyramid, with a angle here of less than 109.5, because 109.5 is an ideal angle, is an angle for ideal tetrahedral, but this is no longer ideal because this lone pair is pushing these 3 bonding pairs further away from itself, so this bond angle is less than 109.5. Going on next to AB2E2, 2 bonding pairs, 2 lone pairs. Again, you start with tetrahedral, but 2 of them are invisible. What you end up with is just a bent structure. And this is what water looks like. Because water, if you draw the Lewis diagram of water, you're going to have oxygen in the middle, one hydrogen, and two lone pairs of electrons. And the two lone pairs of electrons occupy very, very huge space at the top. And this angle is a lot less than 109.5. Yeah. Next is the case of AB4E, four bonding pairs, one lone pair. So four bonding pairs and one lone pair gives you a situation like this, where with the lone pair you have a trigonal bipyramidal, and remember this is an invisible lone pair. So what you have is like a distorted tetrahedron or a seesaw. If you twist this to the other side, you're going to have like a seesaw. This is the base of the seesaw. This is where one person sits, and this is where another person sits. So that is a seesaw. An example of that is a molecule SF4. Next is AB3E2, three bonding pairs, two lone pairs, and you always will see for trigonal bipyramidal situation, the lone pairs will locate themselves on the horizontal plane, because this is where it has the highest or the biggest bond angle, 120 as opposed to 90 only. So the two lone pairs here, there they are for ClF3. The two lone pairs here will be pushing the three ClF bonds far away from themselves, and this bond angle is a lot less than 90 degrees. Well, it is a T-shaped geometry, yeah? Because if you can recall, from here to there is 90 degrees, an ideal trigonal bipyramidal. From here through A to B is 90 degrees. So what actually happened is this angle becoming smaller than 90 degrees due to the big repulsion from the lone pair of electrons, the lone pairs of electrons there. The next situation is when you have AB2E3, two bonding pairs, three lone pairs, and you end up with this linear molecule. All the lone pairs are located on the horizontal or on the equator. So you have a linear I3 minus. Next is AB5E, five bonding pairs, one lone pair. So you have this situation, and it is a square pyramidal with this bond less than 90 degrees. Yeah, it starts with being an octahedral, but one of the apex is invisible. So what you can see is just a square pyramidal shape with the bond angle of less than 90 degrees. And the last situation that you might encounter is AB4E2, four bonding pairs, two lone pairs, and it's because it is 6, it starts with being an octahedral, but two of these are invisible. So in fact, what you are seeing is a square planar. An example of that is XEF4. So that is how you use VSEPR to determine the shape of the molecule, whether it hasn't got any lone pairs, or in this case, it does have a few lone pairs in the molecule. So for molecules containing double or triple bond, now if you recall, there are some of your compounds having double bond. Now, any double bond has to be counted as one bond. Count the number of bonded atoms. I forgot them off here. count the number of bonded atoms surrounding the central atom. Just count the atom, not the bond. Yeah. And then count the number of lone pair of electrons surrounding the central atom. Use the sum of A plus B to determine the shape of the molecule using the table above. So that is easy, isn't it? VSEPR is really, really quite easy. So this is a short, this is going to be just a short video. I'm not going to go any further than this for this time. And I hope all our examples here are clearly understood by all of you. And then I'm going to discuss later a few questions on the giving you a formula of a molecule, asking you to draw the Lewis structure, and from the Lewis structure determine the shape of the molecule. And I'm certain you have done this before in the previous codes. So that's it for now for VSEPR. All the best, keep safe, and bye-bye. Assalamualaikum.